So centralized program, yes, but with eyes looking around the world. We are fortunate to have 2 cycles per year, and I'll tell you exactly what those are. But when we make a cross, it takes us about 2 years to get lines that are genetically stable in the segregated population from the F2 generation to the F5, where we select for traits that are easily visible, disease resistance, agronomic type, earliness, and so on. And we do that with a system that we call shuttle breeding, and I'll explain it in a minute. Once we have lines that are fixed genetically, we start testing them for yield, for quality, for drought tolerance, for heat, and then we send them around the world for, in some key location, for disease resistance, for diseases that we do not have in Mexico. So that's the overall scheme. The important thing here to see is that it takes us 6 years from cross to final selection, because we have 2 full cycles per year. Any other breeding program will take at least 12 years to do the same amount of work. Why? Because 1 cycle per year. So this shuttle breeding concept that is very, very important for white adaptation. What does it consist of? It's basically shuttling the segregating material between 2 locations in Mexico. 2 highly diverse locations. From November to May, we plant in a station in the state of Sonora, in the desert of Mexico. It's a desert. There's hardly any rain. There's about 120 millimeters of rain that comes in the summer, outside of the growing period of wheat. During the growing period of wheat, we have anywhere between 0 and 50 millimeters a year. But there is plenty of water, or at least enough water, from the irrigation from a dam that they have close by. And that's a very important wheat production area in Mexico. It's about 200,000 hectares of irrigated wheat, and we have a station there that's about 200 hectares. And there, the main diseases that we can screen for is leaf rust and yield potential. It's beautiful to express yield potential. And then once we harvest our material, we go back to Mexico City, close to 2,000 kilometers south, in the highland of Mexico, at 2,500 meter altitude, in a station either called Toluca or El Batan. El Batan is where we have our headquarters. And over there, we plant in May and we harvest in October. So while I'm talking to you today, my technicians are harvesting our plots and preparing to plant in Obregón next cycle. And here in that area, the main diseases are yellow rust, septoria, and fusarium. And the condition in terms of photoperiod and temperature are very, very different. The soil conditions between these 2 locations are very different. So why does it contribute to white adaptation? Because a plant or a family of plants during the segregating phase, where you still can select, you still have a lot of genetic variability to select from, a plant at that stage, if it's adapted, attractive, and very well, does very well in Obregón and then in Toluca, under such widely different conditions, it is highly likely to be adapted to many environments around the world. Okay? So we eliminate all the plants or family of plants that are adapted only to specific kind of environment. And that is very important for wide adaptation, and that has been really the secret of the success of the civet germplasm around the world. The shuttle breeding had first been started by Dr. Borlaug in the 50s. He did not know about this. He was not looking for wide adaptation. Dr. Borlaug was a very impatient man. He wanted to do things fast. So instead of doing nothing over the summer, he said, I'll just plant it near Mexico to advance generation. It was just a mechanism to advance generation fast and have 2 cycles per year. But it resulted in creating genotypes which are really very widely adapted. Okay? For example, my personal theory is that if we had only Obregón, we would be relevant only to irrigated or some high input environments or high rainfall environments. Our varieties would never have been adapted to Mediterranean conditions. It is thanks to this Toluca Obregón shuttle that our material is not only high yielding, has high yield potential, but also adapted to some of the very erratic conditions of the Mediterranean. Okay? So if we are able to provide good material to places like Sicily or North Africa, it is thanks to this shuttle breeding. Now, once we have fixed lines that go through 2 cycles of the Shutter reading, we obviously evaluate them in a preliminary fashion to make sure that they have the yield potential, they have the drought tolerance, and those are very important parameter for wide adaptation. So although we test all of our line in one environment in Obregon, we have ways to simulate many environments. Obviously, by irrigating fully, we have a good idea of genetic yield potential, maximum or optimal yield potential. By withdrawing water, we can select for water use efficiency. By planting late, we can select for heat tolerance, and so on and so forth. So we do have a wide range of conditions that we can simulate and ensure that our line that we distribute are not only high yield potential, but also drought tolerant and heat tolerant. Okay? Now this is very, very important when we look at evaluation of fixed line, to have at least one site that is of high yield potential. Of course, in many cases, you don't have such site, like in Sicily. If you have 2 or 3 years of dry weather, you're not going to have very high yield potential years. But you need to try to find a site that can express the genetic yield potential of a line. Okay. Now a little bit on what yield potential is the ability of a plant to express its maximum potential for production. And to be able to make progress, you need to find conditions that are uniform enough, that are stable enough, that you can detect small differences in yield. Because in most cases, yield being such a complex trait, you're not going to get very big jump in yield. You're going to get small incremental progress. And to identify the small incremental progress, we need to have very, very well controlled experimental conditions. And we are fortunate in our station in Obregon to have basically, it's like a big greenhouse, very uniform soil, very uniform weather, that allow us within 2 years to detect lines that are really better than what was there in the past. In other environments where you have erratic weather, you don't have such a controlled experimental condition, you need maybe 5-6 years to identify a line that is superior genetically to the Czechs, for example. We are fortunate to be able to do that in a couple of years because of the precision we get in yield evaluation and because of the very good conditions we have and the very good experimental farm management that we have. I'll talk more about management later. The other thing that is very, very strange but very interesting about Obregon, and we have done a couple of studies in bread wheat and in durum wheat, where we look at the same group of material tested in Obregon and tested in many different areas around the world. And we have come up with results that is fascinating for me, that the ranking of the genotypes in Obregon correlates very, very well with the ranking of the same genotypes in many different areas around the world. Basically, if you select the 10 out of 50, the 10 best lines in Obregon, they're very highly likely to be the 10 best lines in India and Iran, here in Pakistan, and several other irrigated environments. So we can do breeding out of Obregon for all these areas. That gives us a lot of power to be able to address problem in these countries. But also, which is interesting enough, it correlates also with several stations or sites that are in rain-fed environment, not just in irrigated environment. For example, in North Africa and Tunisia, the station of Tassaut in Morocco, or the station of Beja in Tunisia, the best genotypes in Obregon are also the best genotype in those regions, if diseases are not an issue. So that is probably why we were able to identify material that has been so successful around the world, thanks to our experimental conditions in Obregon. Now, in terms of the results, if we look at what we've done over the last 3 decades, in terms of incremental yield potential, If you look at varieties that were released in Mexico by the Mexican National Program that were derived from Semitic material, we can see that there has been a great, tremendous progress from the 70s all the way to now. And that experimental progress continues. These are data from maximum yield potential trials shown or evaluated by our agronomy program, not by us. Just to look at evolution of yield potential. You can see that it has been increasing. So experimental yields are always increasing. And if some of you have heard many people, including the FAO, complaining about yield plateau, that yields are not increasing anymore like they did after the Green Revolution. It may be true in the level of national yield, even though I don't think so, but in terms of genetically, under experimental conditions, that's not true at all. And this slide is demonstrating. We are still able, 40 years after the Green Revolution, or 50 years after the Green Revolution, to make very, very significant progress. If you look at progress at farm level, these are statistics, official statistics from the Yaqui Valley in the state of Sonora, average of 200,000 hectares of irrigated wheat. And look at the progress that is going on. We're still making quite a bit of progress for different reasons. First, in the 60s it was for stem rust resistance, then it was for dwarfing genes. And now it's more about how the crop is managed. We are still making a lot of progress at the farm level. This is not experimental, this is actual commercial yield progress. By the way, the Yaqui Valley, the average yield last year was 7.1 tons, so it's 71 quintals per hectare, average of 180,000 hectares. That's probably one of the highest yielding environments in the world if you consider spring wheat, 5 months growth. And that has been done mostly through genetic, but also through crop management. So even farmers are still benefiting from yield progress thanks to the breeding. Now if you look at historically what we have distributed around the world, and as I said, our outlet mechanism is international nursery. Every year we send maybe between 30 and 50 lines to a whole bunch of people around the world. And these are the years, collections we send from 1970 all the way to 2012, the average yields of the 30 or 50 lines. We took all of the lines distributed around the world, we put them in a unique yield trial for 2 years, in 2010 and 2011. It was a huge, some 936 lines, and we see every year how much yield progress we were gaining. And you can see it's about 6% per year. Most of the published yield progress data in bread wheat, barley, durum wheat are between 1 and 2%. So when we look at genetic yield potential of our material from the 70s until now, we have doubled it. And that's after the Green Revolution. So again, that shows that our approach, our strategy, much like the strategy of many breeding programs around the world actually, has been able to accumulate more and more genes that increase the yield potential. Again, this is a very, very clear demonstration that genetic yield plateaus do not exist. We are still able, and we will still be able, to make progress in genetic yield potential under favorable conditions. I'm still talking about favorable conditions. And why is that? I mean, it's logical. Yield is determined by hundreds of genes, not by 1 or 2 genes or 3 genes. It's determined by hundreds of genes. There is no way you can accumulate the favorable alleles or the favorable gene in one variety, in one cross. It's going to take you decades. In order to be able to accumulate all those genes, you need populations that are billions of plants. There's no way you can do that. But in time, you keep on adding more and more favorable alleles. So I am convinced, and I think this conviction is shared by many in the field, that there is a lot of yield progress to be made in durum wheat, like in bread wheat, like in other crops, because of how complex it is. But you need to have the capacity, you need to make the process, the selection, and the experimental condition to be able to detect these improvements in yield if you want to keep on this yield progress. So yield plateau does not exist. at least at the genetic level. Now let's go out of Mexico, and the material that we sent around the world, we did a statistical analysis, or what they call now fashionably meta-analysis, of data we received over the last 22 years in some 145 sites, a total of over 800 environments per year, and looked at how yield progressed. And the results are summarized in this slide. Each point here, the horizontal axis, you have 13, 14, 15, etc. Those are the number of the international nurseries that we distribute. They correspond to years, basically. It's from 70s to all the way to 2012. And each point here is the average nursery overall location. So, and it's divided into high-yielding environment, above 5 tons per hectare average, medium, between 2.5 and 5 tons, and then dry or low-yielding environment, below 2.5 tons per hectare average of the nursery. So if you see that here, our material, you take it outside based on data collected by national program or collaborators around the world, we are still making 1.4, about 1.4% per year, which is actually very, very positive given the difference in environment. But even in low yielding environment, a dry environment, you still have about 2% per year yield progress. But you note here that the points, the red points, are not very close to the curve, which means that yes, it is a 2% per year, but really it depends a lot on the environment. The relationship is not as tight as in a favorable environment. But still, on average, we are making progress even in dry environment. So, just to summarize in a few words all of this, we are making progress. We are continuing to make progress, and these results demonstrate it. But we also have some issues, I think, in water-limited or marginal environment in our journal. And this is shown in this slide. These are, again, the maximum yield potential trial, sown and evaluated by our agronomy group. And we look at year of release here at the bottom, and then yield potential. Under full irrigation, this is the same slope or the same progress that we've seen before. It is quite good, no problem. But if you look at under reduced irrigation, we haven't made much progress since the 70s until now, or until recently. So why is that? Well, first reason is that because the genotypes included in these trials, these experiments, are genotypes that were selected for their maximum performance under favorable conditions. But that shows that the highest yielding lines under favorable conditions are not automatically or always the best lines when conditions get worse, or when water gets less available. So, how do we compensate for that? How do we make sure that our lines that are very high yielding under favorable conditions do not collapse, or are also at least good enough under water limited conditions? First of all, let's see how we select for drought tolerance or for water use efficiency. And we will go back with the student and try to define the difference between what drought tolerance and water use efficiency is. But for now, I will just use them interchangeably. So as I said, in Obregon, we are in a desert. There's not a lot of rain. That gives us control, very, very high control over how much water we apply. And we have established some 8 years ago a drip irrigation system that allows us to apply exactly the amount of water we want to simulate the intensity of the stress we want at the time of the growth stage that we want. That gives us a lot of power to be able to simulate any kind of stress, from moderate to very extreme stress. We can simulate stress, early stress or late stress, and so on. And we always end up with results that are pretty interesting. Now, just to show you a couple of photos, these are two lines. One of them has started collapsing early on. The other one is still doing fine. Here it's triticale, but durum wheat is the same thing. If you look at the bottom of the photos, you see the early biomass, the leaves. They're the same for the two varieties. They both started developing okay, but then one completely collapsed, did not even produce spikes. The other one did okay. So these are the kind of extreme differences that you see. Of course, we have to take data, precise data on all of this, but this is just to show you the extreme that we get when we get this kind of, when we use this kind of infrastructure. So now, let's look at some data here. And this is, I think, very important from a genetic and breeding standpoint. These are 366 advanced lines that we evaluated both under full irrigation and under drought conditions. And the yield of these lines is expressed as a percentage of the same check. So when you see 100% of the check, means that the yield is exactly the same as check under both conditions. The check is the same under both conditions. And when you look at these data points, you see a cloud and you see no trend whatsoever. In fact, you see no correlation between performance under favorable conditions and performance under dry conditions. What does that mean? And if you look at over years, here, over about 5 years, we have looked at thousands of lines, both planted both under full irrigation and drought, and look at the averages. Under full irrigation, the averages went from 6 to 8 tons per hectare, and under reduced irrigation or drought, it went between 2 and 4 tons per hectare. And the correlation coefficients between the performance under these two conditions are either moderate in most cases or very low. So it is safe to assume that the genes or the characteristics that give you high yield potential or high yield under full irrigation are very different from the genes that give you high yield under drought. So that's kind of a problem. So what is the solution for that? Well, some people will say, okay, you need to have two programs. One for favorable environment, one for dry environment. That is something that is logical to a certain point, but that's something that I think we believe that will take away some of the wide adaptation we are struggling to get. We will get basically lines that are either, there are too specialized, and we don't want that. Okay? So here, just to give you an idea, basically we would have lines that would collapse under drought, have high yield potential but would collapse under drought, or lines that would always survive but never would give you high yield under favorable years. And none of these scenarios are acceptable. Now let's go back again to the graph and try to dissect a little bit the different parts of this graph. Here in the bottom left part, you got the lines that don't do well under either conditions. These are lines that obviously needs to be eliminated. Okay? But on the top left part, you have lines that do very well under drought, but they are not competitive when conditions get better. These are typical land race behavior. Land races, the old varieties before the Green Revolution or before the work that was done here in Italy, were very tall, very late, and yes, they were drought tolerant or tolerant to marginal conditions. They never died, but they never made you rich either. So they kept farmer always poor but alive. That's, I mean, if we want to put it in this context, that's how I would put it. And then on the other side, on the lower right part of the graph, you have lines that do very well when conditions are good, but that collapse completely when conditions get bad. And we have been guilty of distributing quite a bit of those lines from Senegal, just because we did not have, for several years, the right approach to select for drought tolerance. So no more lines in the bottom right part of the graph. What we are really looking for is these lines on the top part of the right top part of the graph. Lines that are acceptable under both conditions. Beautiful concept, very nice. Is it possible? Is it realistic? As you can see, there's very few points like that in that area. So yes, it is possible, but, and from a genetic standpoint, if the genes that give you yield and and the genes that give you tolerance to drought are different, and that are not negatively linked together physically on a chromosome, theoretically you can combine them together and get a plant that has the best of both worlds. Easier said than done. You need to have a huge program to be able to do that. If you have a couple of hundred lines in your advanced trial and you eliminate the majority, you're going to end up with a bottleneck with a program that is so small that you can no longer make progress. So yes, it is possible, but it's very expensive because you've got to duplicate your testing facilities, your testing infrastructure. But you need to have a very, very big program with a lot of genetic variability for other traits to be able to afford to have this kind of an approach. And again, this is the same table, but here it just shows you the percentage of lines that are acceptable under both conditions in every year we have. So in 2007 we had only 34%. So I had to throw away 66% of my material. Some of those lines were really beautiful under high yield convention. I had to throw away lines that yielded 9 tons under full irrigation, just because they could last completely under reduced irrigation. So it's kind of like throwing the baby with the bathwater, but that's the kind of sacrifice you gotta make to be able to be relevant to conditions that are highly diverse and highly unpredictable. And it gets better over the years, but it depends on the kind of germplasm you have in every given year. But you have to be ready to throw away a lot of material. And again, I repeat it, you need to have a big program to be able to do that. At CIMMYT, we do have a big enough program to be able to do that. That is why critical size of a breeding program is always very important. A lot of people will tell you, you don't need to make 1,000 crosses, you don't need to have 200 hectares of experimental plots. You can do it with less. Be more focused, make better crosses. Evaluate less line, but evaluate them better. No, I'm sorry, breeding size matters. Size of a breeding program, if you go below a certain critical size, you cannot be effective, you cannot be viable in the long run. Specifically for a reason like this. But if you add to it disease resistance and quality, you really need to have a minimum number of lines you test every year to be able to maintain a viable breeding program. Okay? So, just so you understand how much we evaluate our line before we are confident enough to send them around the world. In durum wheat, we evaluate the lines that we send around the world at least 3 years under full irrigation and 2 years under drought. And every year more and more drastically. And so the material that we are sending now is probably we are confident that it will do okay in most environments in most years. Okay? Now, heat tolerance. Heat tolerance is a focus that has been relatively new to us. People talk about global warming. People talk about weather getting warmer and warmer. It's going to be an advantage for Europe, for Northern Europe mostly. It's going to be a huge problem for probably Sicily, southern Spain, Greece, and North Africa. It's going to be a dramatic problem for places like India, Mexico, primarily not just because of the thermal effect, but also because of the lack of water that it's going to generate. Okay? So, how do we select for heat stress? No, we do not heat up our experimental fields. We do not do research in greenhouse. But there is a way that's very simple. We just plant clay. By planting in March 1st or end of February in Mexico, in Oregon, instead of November, we are exposing our plots to very high heat from the beginning, from tillering. It affects tillering, the heat that they have reduced biomass quite a bit. It affects fertility of the florets because it flowers at above 35 degrees Celsius. And it affects grain filling and grain size because the plants fill their grain at above 40-45 degree temperatures. So really it's a way to really expose the plant during the entire cycle to high heat stress. this intensity of the heat stress may not be relevant or may not be realistic for conditions in the Mediterranean, even North Africa, for example, because we don't get that kind of heat stress in this area. But it is realistic for places like South Asia, Central India, places like Sudan, Southern Egypt, part of Bolivia, for example, part of Central America, where they have very high heat during the whole cycle. But still, it gives us an extreme scenario where we can select lines that are really adapted or that do very well under high heat conditions. And if you look at the table, at this graph here, this is the kind of genotype we're looking at. Here, this is actual real data, 2 years data, for 4 genotypes. You have on the left side genotypes that both under normal sowing and late sowing behave very well compared to the Czech. They're all around 100% of the Czech. And you have 2 other, genotype 3 and 4, that do very well when they're sown in time without heat stress, but as soon as you put in heat stress, they collapse completely. On the right side, those are the genotype we try to avoid. On the left side, those are the genotype we try to select. Okay, going back to this table, just to give you an idea of how much variability we turned out to have in our program for heat tolerance. If you look at the line that we evaluated over the last 3 years, under normal sowing, the average yield is between 7.5 and above 8 tons per hectare. Same genotype, you plant them late, you get between 1.5 and 3 tons per hectare. So more than half of the yield, or the biomass also, is lost due to heat. But here we were pleasantly surprised to see that close to half of our line did okay under heat. So we have more variability for heat tolerance and more usable variability for heat tolerance in our program than we have for drought tolerance. So that gives us the hope that we are doing okay for that. And this is how we integrated heat tolerance testing in our program, basically at the 3rd level. It's not the main emphasis yet, so we cannot include it early on, but we will be including it earlier and earlier in our program as we get a better idea of how much variability we have and as we make crosses specifically for heat tolerance. Okay, now we're going to change completely and we're going to talk about quality. Okay, but in the middle there is a big chunk of information that I will talk to the student tomorrow about, which is disease resistance, which is very important and probably one of the most important emphasis in the Senate program. We won't have time to do it today, but we will talk about it tomorrow. Now, I was asked to talk about breeding for quality, and here I just would like.
Excuse me.
Okay. I just would like to give a brief presentation of what durum wheat is used for and how we at CIMIC address the improvement for quality. I would like to say from the beginning that it's very different from many breeding programs here in Italy or in Europe. We don't have the same quality requirement in terms of, we don't deal directly with industry like you do here. So our approach is a little bit more about putting in a minimum level of quality rather than reaching very high quality market or niche market for quality. Durum wheat, most of it is used as pasta, about 3/4 of it, but we have to be aware that quite a bit of durum wheat, about 25%, is used for other products than pasta. These other products are probably couscous, bulgur, or bread products in different parts of the world. And then we have to be aware also that part of the durum wheat is not used industrially. It's used in household level, and especially in South Asia and North Africa and the Middle East. And so the requirements for quality are very different. For us, for CIMIC, since we are a global mandate, we have to address the biggest market and the biggest volume of durum. And the biggest volume of durum is used for pasta making industrially. Okay? And also, it has very well-known quality characteristics that we can act on at the level of the breeding program. A lot of the durum products that are done in household, we don't know what makes it quality. We don't know what's the biochemical or chemical basis for these strains. All we know is that there's very, very different range of quality. But for pasta making, we know exactly what people need, what the industry needs, and we know how to work with them at the level of the breeding program. Now, for many years, the semi-durum program did not have a lot of pressure to work on quality because our main client countries, developing countries, were not aware of quality. Their industry was not sufficiently developed to require or to demand quality, and these countries were more interested in self-sufficiency, in quantity, rather than quality. That is no longer the case. That is no longer the case. If you look at a country like Tunisia, for example, they do have a highly industrialized pasta processing or couscous processing capacity, and they need quality to be able to, of the raw material, to be able to process their products properly. They also, because they don't have access to a lot of high quality wheat locally, even in years where they produce everything they need, where they're self-sufficient, they have to still import to correct for quality. Same thing for Ethiopia. Ethiopia has years where it produces more than it needs, but they still have to import, paying a lot of money from Italy or from other places to correct for the quality. So now, really, it is important for us to address quality even in countries where 20 years ago quality was not that important. So, industrial quality is at the center of our breeding program. Of course, and as I said, we didn't talk about rust resistant, but rust resistant and high yield potential is the big